Okay. So, yeah, we're talking about a simple situation where you take a cart and you push it across a table. And example, you find that it comes to rest after traveling 45 centimeters in 1.5 seconds. Okay? So, you know, the question is, okay, now what's acceleration? Because we need that, because what we want to do is study potential and kinetic energy related to that cart and two magnets and so forth. Okay, so you know, we have trouble with this. Okay, so here's the scheme, and we want to get this down. And as at least one of you said, you know, one reason it takes hours to do some of these problems is you try to put the math pieces together.
That really is what's stopping me on not getting homework done.
The what?
That really is what's stopping me from getting homework done.
Yeah, well, get done what you can. I mean, show me what you've done so I can see what you need me to tell you to.
I have not turned in too many half-finished homeworks.
Yeah, well,
I want to try it.
half-finished is okay. I mean, if you're putting the time in, and I think you are, and you're getting half-finished, I need to see why you're getting half-finished, rather than shooting in the dark, right?
Yeah.
Show me what's going on. Then I can confuse you even further. Okay.
I'm writing down I'm trying to write down in a sentence too and explain to you what I'm thinking and how I'm getting stuff.
Well, that's exactly what I want to see, so show it to me. And if you want to keep working on it, you know, take it over to a copier and make a copy.
Make it messy.
Yeah. And keep working on it. But anyhow, okay. So, so we've got that situation. Now the point I'm making here is, you know how to integrate, starting with the constant acceleration, get equations for the velocity function, the position function, and you've actually done it more or less successfully in your homework, where you eliminate a couple of variables and you get 4 equations for uniformly accelerated motion. So we could solve this problem by hitting the net with that sledgehammer and say, okay, initial velocity is unknown, final velocity is 0, right? Time interval we know, be 1.5 seconds, okay? And we know how far it goes. Well, we know 3 things: how far it goes, final velocity, and time. Okay? And we know that if you have the equation, we should know, because I've seen you do it, but maybe you haven't internalized. You could use the equations of motion with those 3 quantities and solve for the other 2, which would include, of course, the acceleration. You don't need to do that. It's much simpler just to understand with the definitions of velocity and acceleration. But in order to do that, you've got to also include these quantities, which are not included in the equations of uniformly accelerated motion. Sometimes they are. Sometimes average velocity equals Vf plus V naught over 2 is included. Okay? And then you've got maybe 5 equations. I like the idea of formulating it in 4 and always being able to say this. But, you know, the authors that do that, I think good authors, don't have a quibble with them. I just prefer to be able to say this. Okay? Okay, so the point is, that given information, you ought to immediately see, well, I know the velocity and how far it went, so I calculate the average velocity. I know how far it went and how long it took. I mean, if you go 120 miles in 4 hours, your average is 30 miles an hour. That's automatic. And it's even more automatic if you make $60 in 5 hours, you're making $12 an hour, right? Okay? Okay, so we get the average velocity. Having gotten the average velocity, what can we do? Well, we know that the average velocity is what you get when you average the initial and the final. So if the average is 30 centimeters per second, which it is in that case, okay? And the final is 0, what do you average with 0 to get 30? 60, right? Okay, and that's also related to very important graph that we've seen. Here's on whatever interval. Here's your V versus T. You have a straight line, meaning the average, so this segment has a length that's representing V naught. This segment represents VF. This segment right here to the midpoint of the interval to the midpoint of this line segment represents the average velocity. Okay? And that's the only relationship you really need to pull all this together. Because, well, actually there are two things there. Okay, there's your average velocity, right? And here's your change in velocity. Okay? Now the two aren't related. Okay? There are lots of different changes in velocity that give you the same average velocity. Just pivot the segment about this point and you get intervals with the same average velocity but with much different changes in velocity. So, now in our given situation, okay, we're given delta x, delta t, and VF. Delta x and delta t, we get V bar. From V bar and VF, we usually get V naught. Okay? And then from VF and V naught, we get delta V, which we combine with delta T. Which we combine with delta T, get the acceleration, right? This kind of diagram can be helpful if it helps guide your thinking, but every step of this reasoning is trivial. I mean, not trivial, but it's very simple.
Purely definition.
Yeah, well, it's not just definition, it should be intuition too. Okay, definition's going to intuition, but formally, everything that I've done here depends on just definitions of V bar and A. Okay? For uniformly accelerated motion. Nothing I did here fails to come from that definition. And the fact that V bar is VF plus V naught over 2, because that's not the definition here. That's clear. To clarify, the definition of V bar is displacement divided by time. Okay? So I should say and the linearity V versus T for case. That's what tells you that VF plus V naught over 2 equals V bar. So you should understand it formally at this level, and you should use that reasoning a lot. Now there are a couple of cases where you can't use that reasoning, but there are only 10 possible situations where you know 3 of the 5 quantities, okay? And in only 2 of those situations, you actually need to use equations that you know how to derive using a little calculus and algebra, okay? So, you know, the calculus and algebra is supposed to be the hard part. You have a lot of trouble with that. Okay? The calculus and algebra are in pretty good shape. There's some holes in what you know, but, you know, as far as this situation, you've got it. Okay? Or at least you had it last time I looked. Hopefully you haven't lost it.
Yeah, that'd be me.
Yeah, well, if you use it enough, you don't lose it. And if you reinforce it enough.
Why lose anything that isn't nailed down?
Yeah. So you got to solve enough problems, which is why I keep assigning them, and hopefully someday you'll hand them all in. Okay, yeah, does this make sense? Okay, you want to use that scheme, because you can use this scheme in the thing I'm going to ask you to do here in just a little while. Okay.